Now that you're experts on identifying similar polygons, what we're going to do is use this postulate. The title says, prove triangle similar by AA. That's angle, angle. Well, sort of. Mostly we're going to use that similarity, because similarity becomes useful. It's even more useful than congruence. Remember earlier we showed how we could figure out the width of a river using congruent triangles without actually trying to drive stakes into the river? Well, you can also do that with similar triangles, and it's even easier. But first, what does this say here? Well, what this basically says really is that if all three angles in a triangle are congruent, then the two triangles are similar. In other words, they would have the same shape and their sides would have the same ratios all the way across. For instance, if xy were 1/2 of jk, then kl would be 1/2 of yz. That's what it means to be similar, and all the way around. Well, if two of the angles are congruent, we know that the third one has to be. You remember that because they add up to 180. So if this were A and this were B, then this is A and this is B, and they both have to add up to 180. So this here is 180 minus A plus B. That's always true. So if you know two angles in a triangle, I think we pointed this out before, you automatically know the third one. So if two angles are congruent, the third one is also congruent. And when all three are congruent, then we have congruent triangles. Well, not very exciting. And you might have guessed the truth of that, but now we have an actual postulate. And if you want to have some fun, this doesn't have to be a postulate. You can prove this. But if they want to call it a postulate, well, cool. That makes it easier for us because you don't have to prove postulates. They're just accepted. So we have another fact we can use now when working problems. And that is, we don't even need to show that three of the angles are congruent. We only have to show the two. Because if you've got two, you've automatically got the third one. And if you got three, you have similar triangles. So what the heck can we do by knowing that two angles are enough to produce similarity? Well, suppose you had a tree and you want to know that it's not taller than the legal limit of trees in your area. Yeah, some places have regulations about how high a tree can be. I'm not sure how much attention the trees pay to that, but the people have to. We know that the tree casts a 50-foot shadow. What good does that do us? Well, suppose we stand over here, and suppose you're 6 feet tall. You stand here and you cast a shadow that's 3.5 feet. Well, again, so what? We got a shadow here, we got a shadow here. What's that do for us? Well, for one thing, assuming we're standing straight when we cast our shadow, this is a right angle. And I just modeled the tree as a straight line. So, the straight line here forms a right angle also. Now, I admit a tree may jut off this way and then come back. Tree trunks aren't always perfectly straight, but you can model them as a straight line. It's actually a reasonable approximation. You'll get your good answers. What about this angle here? Well, there's a sun up here. It's shining, and here you're blocking the light. And at this angle, well, this is the angle at which the sun is shining. Well, it's the same sun is shining on this tree as is shining on this person over here next to the tree. So the shadow is being produced by the same illumination source. The distance between these two is so insignificant compared to the distance from the sun that we treat the two angles as if they're identical. Remember, if we had something like a flashlight and we're only a few feet away, and we had something here and then something else over here, the two angles would not be the same. Because say this was 2 feet from the flashlight and this was 6 feet from it, you would see a large difference in the angles of the shadows that were produced. With this angle here. But when you're talking about something that's millions of miles away, and you're standing, say you've got a separation of 5 feet between you and the tree, that 5 feet is completely insignificant compared to the millions of miles between you and the sun. So we can treat these two angles as if they were identical, because if there's any difference in them, probably couldn't even measure it anyway. So, if this angle and this angle is congruent to this angle and this angle, I guess I should say are congruent to this angle and this angle, we know that these two triangles are similar. Well, now we got something. If these two triangles are similar, then the ratio of this shadow to this shadow should be the same as the ratio of this height to this height. Well, that could work. Let's see here. How about... So it would actually be fairly easy to figure out how tall this tree was by just setting up your proportions, which is 3.5 over 50 is equal to 6 over x. That's this over this. We do our multiplication and get that 300 is 3.5x, or x equals 85.7. So this really big tree here is over 85 feet high. Over here, obviously, it doesn't have to be a human being. Human beings work because most of us know how tall we are, so you know this vertical distance. But if you have a stick, which you know is 6 feet, well, let's use the stick. And there's no law says it has to be 6 feet. You could use a yardstick. Hold it upright, measure the shadow. The taller this is, the more accurate your results are likely to be, because there's always a little bit of error in measurement. And the error will have less effect as your vertical height gets larger. But that's a whole different class in error analysis that you don't need to worry about right now. If you ever actually do this, shoot for something around 6 feet. And when you get to college, you can figure out why you get a slightly smaller error that way than if you used a yardstick. And here's another one of those. Well, forget that. A postal employee messed up. I don't know about you, but they hardly ever get my mail, right? I went down to my P.O. box not too long ago, and there was a note in there that said it was full, wouldn't hold any more mail. Gee, that's weird. I'm popular, but I'm not that popular. So I went in to get my mail and sorted it out right in front of them. Over 50% of the mail was not addressed to me. I pointed out that my box would fill up much more slowly if they would only put letters actually addressed to me in it. I don't know. Didn't seem to make much difference. I kept getting mail addressed to other people. So, we have this postal employee who got this all wrong. He figures that by the AA similarity postulate, these two polygons are similar. Well, this postulate applies to triangles, and these are not triangles. In fact, these are called quadrilaterals, and they may or may not be similar, but you can't prove it by only having two angles. So this is The big problem here is that he tried to apply a triangle postulate to a quadrilateral. You can't do that. Now here's one where first we have to figure out if these two triangles are similar. They certainly don't look congruent. In fact, forget that. Let's just see if they're similar. Well, for that, we need at least two angles to be congruent. Now, this is a pair of vertical angles. So these two, this angle is congruent to this angle. That's one pair. Now we have to find another pair. But these little arrows here, they're there to tell us that these lines are parallel. So what does that make this here? That makes this a transversal cutting two parallel lines. And that means that these are alternate interior angles. So they're congruent. And in fact, I could have used this as the transversal and pointed out that these were alternate interior angles. Either way works. The point is, as long as we get two that we can show are congruent, we've got similar triangles. Now that we have similar triangles, we just have to identify our corresponding sides. The corresponding sides are in the same ratio, but is it this side and this side, or this side and this side? Well, if you want to match them up, look at the congruent angles. This is opposite this angle. This is opposite this angle. So, let's say that P here corresponds to 10 and 12 corresponds to 24. So, we can write P over 10 equals 24 over 12, if I got this right. P over 10, 24 over 12. That, of course, equals 2. So, P equals 20. Kind of makes sense. We doubled this one, so we doubled this one. The trick of this one was spotting. Remember, you had two parallel lines here. The transversal produced alternate interior angles, which are congruent. You see, all that boring stuff we learned earlier, now we're using it. Oh, and by the way, that means that the answer, of course, is B. Maybe I should have mentioned that. There it is. B is the right answer. Okay, here we have another one of those. The mailman made a mistake. What did he do wrong here? Well, we've created two similar triangles just by drawing a parallel line here. Here's this triangle, and then the big one here. So we have a similar triangle, in a sense, contained inside the larger triangle to which it is similar. So what did he do wrong? Well, 4 to 6. Pardon me, that's not right. The proportions we're looking for are this long side to this long base should be the same as this cutoff side to this line here. Well, this large one here isn't 4, it's 9. So what we need is 9 over this. Pardon me. This is I added some labels here and redrew this small triangle over here. So we can keep in mind that we're talking about two separate triangles. Well, not so much we as me. I was managing to confuse myself so much I was starting to forget my own name. I just took this triangle here and just moved it over here. So let's talk about this little triangle and this big triangle, okay? Now this little one, we know, has side 4 and side, and let's call that the base since that's the horizontal one. So we'll say that has side 4 and base 6. Now we compare that to the larger one. We know that they're similar because of the way we drew it. When we cut it with a parallel line here, we automatically produce two similar triangles. But the ratio we want here is this whole side over this one. In other words, we've got the ratio of this to this side. In other words, the ratio of BD to BA equals the ratio of DE to AC. Ratio of the small one over the big one is the same as the ratio of this small base over the larger base. Now we can put some numbers in. You were probably never confused, but I was starting to confuse myself. So for BD we've got 4, for BA we've got 9. DE, well that's 6, and AC is X. And if I do more work over here, as you can see we get 4X equals 56. 4X equals 14. Is that right? I hope so. This is the proportion you want to set up. By the way, if you don't remember how we know that these, I don't remember if we showed it or not. Why is it when you just draw this parallel line you automatically produce two similar triangles? Well, this angle has to be congruent to itself. It's shared by both triangles, the small one and the big one. So that's one congruent angle right there. What about, say, this angle and this angle? Well, here we go. We've got two parallel lines cut by a transversal, and these are corresponding angles. So they're congruent. So now we've got another pair of congruent angles, and we're done. That's why you can always draw a line parallel to one of the sides and separate this into a smaller triangle, which is similar to the larger one. If this line wasn't parallel, then it wouldn't be true. You can't just run around breaking up triangles into smaller ones and assume that they're going to be similar. But if you use the parallel line, then yeah, that'll work. Well, at this point, it should be quick and easy to spot that these are two similar triangles. Remember, we've got our vertical pair here, which are congruent. And since these are parallel, they're cut by transversals, and we've got alternate interior angles. That's always going to be true. We got to set up like this. We get two lines crossing, and then we cut them off with two parallel lines like that. Boom, we've automatically created two similar triangles. Hardly even had to try. Now, what they want to know is the length of BD. That's the whole thing. Well, I think we're going to have to find X before we can do that, aren't we? And remember when we set things up like this, we figured out from the last problem we did like this. This angle, let me just draw it in, is congruent to this angle. So our proportion should be this side to this side is the same as this side to this side. So we get 3 over 4 equals 5 over x. Or 3x equals 20. X equals 20 over 3. I would put that in the fraction, but I've noticed that the answers they're allowing us to choose from are all in fractions, so might as well leave it. Now, this, of course, we got 20 over 3 plus 5. Well, we can write 5 as 15 over 3, right? Plus 20 over 3, because what they asked for was this entire length. They didn't ask you for x. See, 20 over 3 is here. Yeah, they did that just to mess you up. And on a test, when you're in a hurry, by the time you get done with all the calculations and find x and spot it over here, you'll figure that's the answer. And they will have got you again, because that isn't the answer. They're asking you for the whole thing. First you find x, then you add 5 to it, and that of course is 35 over 3, and that's that one there. So once again, they put the likely wrong answer in there to try to trip you up. Don't let them do that. Now let's see here. With this one we've got a whole bunch of information. Gee whiz. Take me the rest of the year just to figure out what all this means. Oh, wait a minute. Why don't we do what they say down here? That's a good idea. Let's write everything in so it makes sense. AE is 6. Hope I've got room. Okay, there's 6. AB, that's 8. CE, where is that? Ah, right here. And DE, that's 10. Oh, well, that's not so confusing now, is it? And what about AB parallel to DC? Okay, so here's AB. Let's draw in our little parallel thingies. I think they're also called arrows. Arrowheads. These two are parallel. Okay, now we know what we're talking about here. Kind of looks like a bent kite, doesn't it? Well, let's see. Well, that's 2 pairs of congruent angles in the diagram. Well, this is too easy. There's lots of congruent angles here. Remember, vertical angles are congruent, so we got a congruent pair here. And a congruent pair here. On the other hand, if these two are parallel, then this transversal produces alternate interior angle pairs, which this pair and this are congruent. This one, oops, no, we can't say this one is, because that takes off. If this one continued on and there was an angle all the way around here, that would be congruent. But so this is definitely not congruent to this one. What else can we look at here that's congruent? It looks like this angle and this angle. So here's 1, there's 2, 3, about 4 congruent angle pairs actually. The 2 pairs of vertical angles and 2 of the 4 interior. Alternate interior angles. We don't have alternate interior angles all the way because of the way this takes off here, over here, and similarly here. Name a pair of similar triangles. Well, see if we got room. Boy, that's awful. Okay. Well, these two are congruent. And this angle is congruent to this angle. Wait a minute, that's not right. This angle is congruent to this angle. These are the alternate interior pairs. Well, that means that this triangle here is similar to this triangle. We've got these two angles are congruent, and this angle are congruent. Two congruent angles means similarity. And what about these two? Well, these two are congruent. Can we find angles here? Well, all they asked for was a pair, and that's a pair. So the top and bottom one, those are both congruent. I'm not too sure about these, because this is not an alternate interior angle to this, because of the way this line drops down here. And down here, same problem. We don't have an angle with the parallel line. We just have it here. They asked for a pair, and the top and the bottom would be the pair. And your similarity statement would be like that, I think. I hope. And the last part, and the similarity statement, I really should have written it this way and matched up the congruent vertices. For instance, this angle is congruent to this angle, so B and D match up, so I should have written BAE and then DCE. Put everything in the correct order. It's slightly more accurate than what I wrote before. Now we got to find BE and DC. Well, let's see here. DC is this one, which they didn't give us. Okay, good. That means the question makes a lot more sense. And this one here, they didn't give us either. But that's not a problem. This one here, remember these top and bottom triangles are similar. So if we call this X, we can write that 8 over X equals, let's get our similarities right. Well, these two are the congruent angles, and opposite them is the 6 and the 15. So the ratio of this side over this side is the same as the ratio of this side to this side. And that gives us that 6x. And if we just go ahead and do the algebra, 8 times 15 equals 6 times x. So we get 120 equals 6x, or x equals 20. That was DC. Now we can do the same thing up here. Didn't they ask for BE? Yes, they did ask for BE. And in this case, if we call BE y, then we have that y over 10 equals, now we have choices. We can use 6 and 15 or 8 and 20. So, I didn't do a very good job of leaving myself room here, did I? I moved it over a little bit to get y over 10 is 6 over 15. There's 6 over 15. There's the y over the 10. 15y equals 60, or y equals 4. That's BE in here is 4. And that's all there was to it. There are these problems, especially with all this stuff up here in the front. They look tough, but just take it one step at a time. That's why they call it a multi-step problem. And in the books, they break it up for you. For instance, you might have gone through some of these steps if the only thing they had asked you for is find BE and DC, because you'd have to figure out that they were similar by identifying congruent pairs. And when you found the pairs, you'd have to identify the the similar triangles. Once you have the similar triangles, then you can use the proportions to find the unknown lengths. They told you what steps, and that's good. That's good practice. When it gets to the point where nobody tells you what steps to use, hopefully you'll remember this kind of stuff and break it up on your own, much the same way they did. Here's an easy one. Explain why all equilateral triangles are similar. I think I showed you before that all squares are similar. Well, same reason down here. Remember we figured out earlier that equilateral triangles are also equiangular, and each angle is 60 degrees all the way through. And same thing here. All equilateral triangles are all 60-degree angles, which by our angle-angle postulate means they have to be similar. And that's about all you had to say. Now here's one of those explanation problems. Why is it you can pick any old 2 points? I bet if you were to work backwards, you'd find that similarity is actually related. But let's not worry about that right now. Here we have a line. Okay? Well, what we can do is just create a couple of similar triangles. Well, first off, how do we know these triangles are similar? Good question. Well, this is a right angle here, and this is a right angle here. Well, okay, we're halfway to our angle-angle postulate. Now these are two vertical lines. That means they're parallel. They're both vertical. If they're parallel, then this is a transversal. This angle and this angle are both corresponding angles. That means that they're congruent. So now we have similar triangles. So far so good. Now the slope, let's say from here to here. What is it? It's this distance here, this rise over the run. In this case, we have the change in the y coordinate over the change in the x coordinate. So I'm going to write it like that. You ever seen that before? Delta y. That's not triangle y. That's delta y over delta x. That's the change in y. So if this whole thing here, we got change in y here, the change in x right here, that would be our slope. Well, what about this tiny rise here and this run here? If this is our delta y, or this one, will these two give us the same as this one? Will they each give us the same answer? Let's check it out. I drew in some labels here. Let's call this vertical part of our triangle A, and this horizontal line is B. Our other similar triangle, A prime and B prime. Now our slope is going to be A over B, or A prime over B prime. We can start with our similarity relationship, which tells us that the ratio of say A prime to A is the same as the ratio of B prime to B. So I just wrote that out over here. There's our similarity ratio. But we can exchange the means, can't we? So now we've got A prime over B prime equals A over B. Oh, wait a minute. A prime over B prime, that would be the slope from here to here. A over B, that's the rise over this front. That's the slope from here to here. Well, okay, we went from here to here, or from here to here, and we got exactly the same answer, which is what we were supposed to show, I think, that we can pick any 2 points. Well, that's what we did. We pick a point here, and this point, or this point and this point. Doesn't matter. Because of the similarity of the triangles, we're still going to get that this A over this B equals A prime over B prime. And I really didn't even need to put this in here. Sorry if I confused you. All we need is these two triangles here. We didn't even have to compare it to the larger one. I thought I was going to have to show that these both actually turned out to be an accurate slope, but that's not what they asked for. They just want to show that the slope from here to here, or from here to here, has to turn out to be the same, using similar triangles to show that. There were many other ways to show that result. Did I mention before there's more than one way to solve a math problem? Well, that's about it for now.